Hello everyone, welcome to this section of networks in R, and we'll be showing you how to plot some networks and do some bit analysis like detecting communities using some algorithms and plotting some degree distributions and how you will project a bipartite network into unipartite network and then uh, plot the networks. We'll be also showing you how to convert the normal adjacency matrices to GraphML formats, and then also you can import the GraphML formats to other tools such as Cytoscape and Gephi. So to do for this exercise, I used the drug target network, which consists of 727 drugs and 3519 proteins, and it's um, a dichotomous network, which means that it contains either zeros or one. You can also call it as a binary network. Uh, for this tutorial, I'll be using the iGraph library, and the iGraph library is a pretty powerful library which is built on the RBGL, which is the Boost Graph library, and it has a lot of functions. For example, competing communities, modularities, searching, do depth first search, breadth first search, and like lot of functionalities. You can just go to the Google and type the iGraph. You can see you you can go to that page also, and it has also the Python extension Python API as well as the R API. So for this tutorial, I use the dbprot as the file name. I load the data here. So let me clear the console for you. So okay, I load the data, and since the data is a data frame, and to project the network in two dimensions, for example, the drug and the target, you need to convert into a matrix because the transpose works in matrix, the matrix multiplication. So I convert the network into matrix. Now the projection which I am doing is I'll be creating two separate networks of protein and the drugs. So I'll tell you what the bipartite network here is. It consists of 727 drugs and 3519 proteins. So two drugs are connected if they are connected by a single protein, and so as two proteins are connected if they are sharing a single drug. So this is how you project the drug target network into two separate networks. So for that, what I did to project, I just did a matrix multiplication of the just it's called the inner products. Like for example, the protein, since the rows are you can when you do the dim net, the rows are the proteins and the columns are the compounds. What I did for the protein, you just multiply this matrix with the transpose of that, and it converts your net in your matrix to only protein and protein. So when you do dip protein, so it has 3519. It's a square matrix of only proteins share which share the compounds. So now what you do, you will find two proteins, for example A and B shares five drugs. So here, if what I said, to convert into a binary matrix, you only convert all the numbers which are greater than 0 to 1, and the remaining 0 and the zeros will be 0, but all the numbers which are greater than zeros to 1, which indicates that two proteins are connected if they share a single drug. So this is how I converted it. And to remove the self loops, you can you use the diagonal command, where you remove the self loop and just give that as 0. Same for the drug network. So I transpose it first, so it has 727 cross 359 matrix. I multiply with the 3519 727 matrix, and it gives me the drug network. And similarly, which are greater than 0, so two drugs are connected if they share a single protein. So, and also I remove the loops here. And once this is done, what you can do, you can just convert the matrices into iGraph objects. So for the iGraph objects, you need to use the graph dot adjacency command. So the matrix of proteins is saved in the protein variable, and the drug is saved in the drug, and the mode is undirected. You don't want any directed nodes, and there is no diagonals, so it's given as false. So now I have two iGraph objects, which are the networks, and now I can play with all these networks quite easily. I can decompose the graph into now number of components, which contains minimum vertices of 2. See, I just decomposing the drugs and the proteins, and when you type it, uh, so for example D, it shows that there are 25 components. Here for the first component, it shows it has 527 nodes and 7637 edges, and next one has 7 and 21 edges, next one has 5 and 7, and so on. Similar for the proteins, you can also just type and just see. And if you want to calculate the diameter of the each components, you just use the sapply command. Here is pretty simple. Compounds are t and the diameter function, so it will calculate the diameter for all. So the first one is just 1, it's 10, then 1 and 2 and 3, 4, and similar, and so on for the proteins also. We want to calculate the clusters, so the of the G drug, uh, these are, so they have 113 clusters. The maximum has 527, so it is quite similar to the number of components it founds. So also for the protein, it has 2965 uh, clusters here, and one of them has 439 nodes in it. And you can also use the number.cluster command to see the number of clusters for the drug, and this one is for the protein. You can also calculate the betweenness, which is defined as the number of shortest path between the two nodes. Means a node which actually comes in between lot of other nodes. So those that is known as the betweenness. So I actually created a data frame and put it here, and then I order it. So order the data frame based on in descending order. So head, so this one has the highest, amitriptyline has the highest betweenness, diclofenac has the lowest betweenness, and so on. So this goes on in descending order. You can also calculate the graph density, which is the ratio of the number of edges and the number of possible edges, and it shows it has a pretty low density here. You can also search for the clicks. Now this algorithm will take a long time, I won't show you, but you can try with short networks like 100 nodes or so on, with minimum of 3 nodes, because a click has a minimum of 3 nodes in between. You can also increase it to 4, 5 and 6. So as you increase the min, the computation time increases. So I won't use it because I have a long big network. It's still big for local machine. You can use any server uh, uh, to, to run the click function. There's also a community detection algorithm to detect the number of communities. This is a crude algorithm which was developed by Aaron Closet and Mark Newman, and this has the order of m plus n to the power n into n, and maximum of like order of n square on a sparse graph. The function can be accessed by a fast greedy community function. So I am searching communities in the drug network here. So the community is done. It's pretty fast, and the membership command shows you the compounds and which community does it belong. So for example, piperacillin, it is in 13 community, pipitazine is on the second community, and peroxisam is in the first community, pramixazole is in second community. So piperacillin, pramipexole belongs to the same community, so as prazosin here, so as prochlorperazine. So all this indicates it's a kind of clustering, you can say, but the way so it's you can look at the paper of this. It's by the Aaron Closet, and you can go on this query the fast3D in the help box, and it will point you to the paper what they have used. Also, there is other way of finding communities using the random walk based is in the random walk based methods. And if you want to search a community for in the G drug, in the drug network of minimum number of steps. For example, if you have 5 nodes, and oppose and A connects to B, B connects to C, C connects to D. So only those steps will be considered. So for one, A to B 1, B to C, another one is 2, and C to D is 3. So detect communities based on the number of steps. Uh, so I compute it, and the which max size will give you uh, the maximum size of the community here, and you can form a table also. It shows you the 15 index has 125 nodes here, and you can extract that network only. For example, if I want the fourth index, which has 27 compounds, I can extract it as using the induced dot subgraph function. So induced dot subgraph extract the nodes from the G.drug matrix where the membership is 4. So I extracted all the nodes which of the membership 4, and when I can plot that. See, I just plot it here, and it shows me these are the drugs from the membership 4, which is detected by the walk trap community algorithm, and then you can just play with that. So this is how you extract subgraphs from the drug network using uh, induced subgraph function. You can also see the sizes also gives you the the size of each member, which does it belong. There are also other measures. If you want to measure the centralization of the whole network, you can use centralization degree, pass the network, and just extract the centralization variable. So centralization degree computes all the thing here, like the closeness. There is centralization degree, centralization closeness, centralization eigenvector. Uh, so I computed all these things. It's pretty handy measurement tool to figure out how much dense the degree tells you how much dense the graph is, or how much close the nodes is. It's something it's pretty useful in doing in detecting in deciding the threshold. You can also do plot the degree distribution. So you just use the degree function, and then this degree dot distribution function computes the cumulative degree, and to plot to see whether the degree distribution fits a power law or not. You just need to compute it using this power law dot fit function and just pass the degree values to this with the minimum x min of 20, and you can plot the degree distribution here and the lines, and you can see the lines here, and it shows whether it is a scale free or kind of that kind of network or not. So you can also see the neighborhood of a given order of a vertex v, which includes, like, if you want to find which are the neighborhoods, how many neighborhoods does the node risperidone have, it can show you like there are 110 neighborhoods. And if you want to just, you can pass any drug name, actually the labels, and just try to see which what are, how many drugs does it connect to. So this gives you the, it gives you the kind of degree distribution for it's a kind of degree measure for each element in the, for each node in the drug matrix. So we can also plot the drug network. So I have shown you here the full example only based on the drug network. You can similarly work out with the protein network here, which I have, which is a separate unipartite network, and just run all these things similarly here. Uh, so plotting the network, I'll be using this layout algorithm, which will lay the nodes in the two-dimensional pattern. So this is a quite known algorithm. It's Frachman-Rengold algorithm. I will apply on the drug network. Then I color the nodes based on the membership. Then I try to plot it. Remember, when I am plotting here, the FGCOM is from the, is the community, so I'm plotting also the communities along with the network. So you can plot the you can pass the FGCOM the community results here, then the drug network, and if you want the vertex of size 2, and you can also give, there are other layouts here, like I use Kamadakawa, you can pass the layout equals to L here, which will plot this network here, and also the edge width, which shows the number of edges, the size of the edges, and you can also color the vertex here, and so on, and also label it. So when I zoom it, it shows you the net, it shows you a nice plot of the communities of the network here. Similar, so remember I use the community from the fast greedy algorithm. We want to plot the eye graph for, and there is other way of plotting it. For example, if I'm plotting using this layout algorithm, but I don't want the communities anymore, so it will be colored based on the membership here, as you can see. So it is being colored in the form of membership. It's a very beautiful plot here, and you can save it in high dimensional using the export command as PDF, and just you can just make it more. You can just say it is 7 and then 5, and just you can just save it. If you want to plot the walk trap community detection algorithm based on top of this plot, you can use this. So simply pass, same as like if the FGCOM, you can pass WLCOM and pass all other values the same. The size of the labels is maintained by this vertex level dot says variable. You can decrease it or increase it. It will, as you increase it will be bigger, as you decrease it will be smaller. So now once you have done, you can just plot, you can save as PDF, and also there are various formats of saving this file. and like in edgeless format, PyEC format, LGL, GraphML, Dymax, GML, Dot, and Leda. So most of the tools, network-based tools like Cytoscape, Gephi, accepts the GraphML and the GML format, and even the dot format. So what you do, you just write the graph. For example, this is my variable name, the graph file name, and I wanted to save it as GraphML format. So just write dot graph, it will save it as it on that GraphML format. So now the problem in this net in R is like you cannot play with the graph nodes, like you cannot hold a graph node and just move here and there. But in other good tools like Gephi and Cytoscape, it's pretty handy, and it's pretty user friendly. Like you can play with it, and can zoom it quite easily, and zoom in and zoom out. So now it's up to you, like what you want to use, but for this course, uh, we will be using mostly we are using R. So if you want to play with the other tools, you can go ahead and just save the file and just play with that. So once you're done, you can save any file in GraphML. You can also read the GraphML files using read.graph function, and once you read it, you can save it in a variable, and then it's just simple. So it has read the graph, and now what you can do, you can use that variable and pass it anywhere. So you don't need to use a graph.adjacency anymore. You can start with compounds.t and decompose graph.g, so something like that. So no need to use the graph.adjacency because it has already converted the object into an iGraph object, and you can just directly start from here. I hope you enjoyed this tutorial. Thank you.